Hello everyone, welcome to the talk presented by two researchers from our strategic sponsor Allegro. Let's give a warm welcome to Kalina Jasinska-Kobus, who is a research engineer and also a PhD student at Poznań University of Technology. Her interests involve extreme multi-label classification, and also Bartosz Ludwiczuk, who is also a research engineer, and he focuses mainly on face recognition and metric learning techniques. Remember that you can ask questions in the stage chat, and we are going to forward them at the end of the talk. Welcome and enjoy.
Hi, I'm Kalina, and as you already heard, we are both with Bartosz research engineers at Allegro. And we are happy to be with you here today and meet you all during this ML Intel virtual event. Today, we are going to talk about deep metric learning, more precisely about triplet laws and batch construction strategies. Our talk will be focused on the research problem we both work during our research time. However, you will soon see that deep metric learning is not just one of the research topics we work on at Allegro, but also a tool we use from time to time for production purposes. Sorry. Yeah. Deep metric learning usually focuses on creating an encoder. Such encoder transforms an object or a photo, for example, of a jacket, in this case, into a vector of numbers, which is an embedding. The goal is then to create the encoder such that it will embed the objects in a space in which the distance between the objects corresponds to their semantic similarity. In case of those clothes, similar jackets should be closer to each other than a sports jacket to a high-heeled shoe. Such encoder is created based on objects from the available training classes. However, we want this embedding to generalize well to the unseen ones. Such embedding not only locally models similarities of pairs of objects, but also allows us to visualize a meaningful global structure of the data, like on this T-SNE visualization of clothes. Why having such embedding is important? Deep metric learning is, in fact, a tool, like a hammer, that allows us to approach various problems like classification, few-shot learning, zero-shot learning, personal identification, detection of novel classes, clustering, retrieval, or recommendation. So let's go through several real-world applications of deep metric learning. FaceNet, deep face, or open face use deep metric learning to obtain representations of faces. Such face representations may be used for various purposes. For example, having a database of annotated face representations, one can identify a query person being similar to the stored face representations, or detect an unknown one, dissimilar from the stored face representations. Another application of deep metric learning is retrieval, like visual search at Allegro. Having representations of available items, like clothes in this example, one can search them with the query item and retrieve the most similar items. This way, instead of typing a lengthy and ambiguous description of a clothing item into the search bar, one can just upload a photo and a photo of interest presented in the upper parts of those screenshots and retrieve the most similar items among the offers given in the bottom part of those screenshots. A similar application of recommendation. For example, recommendation of YouTube videos. In this example, the leftmost column gives the query videos, and the columns on the right, those that were most similar. In certain task-specific way. So in all those applications, deep machine learning techniques can be used to find items similar in some task-specific way to the query items. So far, we said that we create the embedding, the encoder based on the training classes, but evaluated using novel classes. So for clarity, we will go through the evaluation procedure used in deep metric learning experiments. In the test sets of the benchmark datasets, there's a number of novel classes. To obtain single data point, we sample some of those novel classes and select the items corresponding to these classes. And then we select one of these items as the query. Then we embed all the objects and find K, for example, 2 closest items. Then we usually evaluate a metric named recall at K, which differs from the most common understanding of recall in classification. Namely, in deep metric learning, recall at K is 1 if at least one relevant item was retrieved in those K nearest neighbors. So an example from this slide, where first the nearest neighbor is an incorrect from the incorrect class, and the second nearest neighbor is from the relevant class. Recall at 1 is 0, and recall at 2 and all other case is 1. Then you'll of course average the results of many trials. Also, metrics relevant for evaluating the quality of clusters obtained using the embeddings produced by the encoder are used. For example, normalized mutual information. However, this metric is rarely reported right now, so by now we skip it. Let us now comment on the relationship between deep metric learning and other machine learning paradigms. There exist several similarly named areas: similarity learning, metric learning, and deep metric learning. The first, similarity learning, is the most general one. It captures the methods of learning a function measuring how similar two objects are. Metric learning is more specific. It restricts the learned functions to distances or metrics, obeying relevant axioms. Many methods in this area use linear transformations of data and are thoroughly analyzed. Finally, deep metric learning uses deep networks to extract features, create embeddings, or predict the distance, and this way allows us to learn similarities of complex objects like images. What about other areas of machine learning? In the beginning, we said that we consider classes of similar items. So why do we talk about some deep metric learning, not classification? Remember that we need generalization to new classes, which is not standard in classification problems. We also said that we create embeddings of objects. So what about representation learning? This is, in fact, a much wider area, consisting of supervised and unsupervised methods, and the deep metric learning is just a small subfield of it, besides many other advanced techniques. Interestingly, recently on the self-supervised learning workshop during NeurIPS, there was a paper considering a similar problem to the one we work on, but in the context of contrastive learning of representations. So let's now move to an overview of the learning process in deep metric learning. From now on, we will use images of cars as the examples. These images come from the smallest benchmark dataset used in deep metric learning experiments. This dataset consists of images of cars. And a class corresponds to the model of car. So the images coming from the same class may differ in the color of the car, the aspect, or the background. So in case of the images of the slide, the first two from the left come from the same class, and the rightmost from a different class. As we said, we need a function or an encoder denoted with f on the slide that transforms the objects from the original space to a space where the distances correspond to the semantic similarity of the objects. We usually start from a randomly initialized or pre-trained encoder and then try to improve it by training. So that instead of this encoder placing dissimilar items close to each other, we would like to have this one placing similar items closer. How to train such encoder? What loss should we use? An example loss expressing our need is the triplet loss. This loss has three arguments: an anchor and a positive being similar to each other or coming from the same class, and a negative item dissimilar from anchor and the positive. This loss is 0 if the negative item is further by at least a margin m from the anchor than the positive item is. If the negative item is closer to the anchor, then this loss is non-zero. A triplet that has a non-zero loss is called an active triplet because it may contribute to the training via non-zero loss. To update the model efficiently, we would like to have a batch of triplets. However, the training data usually consists of simply images coming from different classes. For example, on this slide, each row of images presents images from the same class. To create a batch of triplets, we usually first sample K, for example, 3 classes, and then for each of these classes, we sample N, for example, 2 instances from each of them. The outcome of this step is a small subset of the training data. We'll refer to this step as sampling. Next, we generate triplets using the sampled objects. We'll refer to this step as mining. The most basic miner creates all triplets that can be created of the sampled objects. Finally, we compute the loss using using this generated batch of triplets. This way, in the process of training, we optimize an objective on observations from the training classes. However, what we finally evaluate is the performance of the encoder on the new classes. So after this introduction, I'll pass this virtual floor to Bartosz, who will delve into details of deep machine learning. Thanks.
So hi everyone, I'm Bartek, and we'll now deep dive into metric learning training pipeline. So in short, the standard metric learning training pipeline consists of 4 basic blocks. It begins with the sampling the data using the sampler, followed by the creation of the triplets by the miner. Then the data is passed through the encoder to get the embeddings, and finally the loss is computed. An encoder can be updated. Usually in the implementation, the encoder is placed right before the miner, as then each observation needs to be embedded just once, and also some sophisticated miners also need embeddings to get the better triplets. However, for the simplicity of this presentation, we present this order, as it allows us to focus on the batch construction strategy. Kalina describes an example implementation of this each block, but there are many possibilities. The researchers in the deep metric learning is focused on the modification of those blocks to boost the performance of the encoder. A lot of losses, besides the triplet loss, were proposed to better capture this metric learning task. Many of them were just proposed based on the intuition or the empirical observation. The losses differ significantly. Sometimes are computed using the free observation, sometimes only just the pairs, sometimes on just one observation. In the remaining part of this talk, we just focused on the triplet loss only. Another area of the research, beside the loss, is the minor. Previously, we described the easiest one, the minor, which just construct all the possible triplets. However, there are many much more complicated strategies, like creating all the positive pairs with the hard negatives, and also maybe the easy negatives. Those strategies are based on the empirical observation that different triplets contribute differently to the training of the encoder. And all these strategies start with the simply sampling k random classes and n random observation from each of the class. And little research have been done on this stage of the pipeline. And during this presentation, we will focus on this stage. Noticed that both sampler and miner, in fact, select the triplets which are used during the training. And this way, they modify the optimized criterion. In fact, if there are two easy triplets, we've got no loss and no change in the encoder. Two hard triplets make the optimization problematic. On the other hand, if we choose only the specific type of the triplets, it may present only certain types of the similarities. Then the optimized criterion is not only determined by the loss function, but also by this batch construction strategy. And the intuition from the empirical results suggests there are some important factors which influence the performance of the encoder. One of them is the number of active triplets, and second one is the similarity of the anchor to positive and negatives, which is currently mainly done using the different mining techniques. But yet it's unclear why and what results in the best encoder. Usually, but not always, the higher number of the active triplets means better encoder. And also some papers claim that harder positive are better and others want the negative. Also, the recent paper from the ICML and ECCV show that many results are not reproducible. And in fact, the many performance gains which our authors are claiming are in the improvement of the encoder, but in this way that they are changing the training parameters, not the change in the miners and the loss change, which is something we should not care as much. And we propose our new sampler, which is called hard class sampler. And the general idea from the sampler is to sample similar classes to each other in a single batch instead of the random one. And this way, it enables a construction of more active triplets in the mining stage, as on average, it produces harder negatives, which will be shown in the next slides. And to work, it needs the class proxies, which are used to measure the similarity between the classes. And the class proxy can be calculated just by average embedding for all observation from the given class. And for example, we go through how hard class sampler works. And this slide, you can imagine that is the embedding space, and the 5 classes are embedded and 4 examples for each class. And for step 1, we need these class proxies. So to get them, we just pass through entire training data set through the encoder, and then just calculate these embeddings, which then serve as the class proxies. Then, to start the sampling stage, we need to choose some random classes. It can be just one, like this one marked with the circle. Then, we chose several classes, which are the one chosen at random, using these calculated proxies. regardless their position on this. And the last step is just sampling the k random examples from each class. And this step is exactly the same like in the random sampler. And if we now all the data is chosen or the observation, we can use the mining stage to create the triplets, which then fed to the encoder and the loss function. So in short, to summarize, this is our idea that hard class sampler chose similar classes instead of the random one to compose the batch and then produce more harder negatives. But how this idea influenced the quality of the encoder? So we've got the plot. There's in the y-axis, there's the recall at 1, which is equal to accuracy, and 3 benchmark data set: cars, Stanford online products, and InShop. And the first column presents our baseline results. It means that we are using just the random sampler, some minor, and the triplet loss. The next column gives the result of the divide and conquer algorithms, this idea, which is also try to make more harder negatives in the batch, but it also modified the loss function. Then it's hard to judge if there is the gain of the accuracy is from the sampler or from the loss function. The next one, cross-batch memory, is current state-of-the-art method. And it also increased the number of active triplets, but it's not without changing the minor sampler. In fact, it enriched the current batch sampled from the data with the batches from the previous iteration, and then it virtually makes the batch larger. And the last column is our hard class sampler. The proposed sampler beat the baseline in each case, and also the state-of-the-art method on 2 out of 3 data sets. Improved the performance of the encoder by just simply changing the sampling stage, especially simple, in fact, compared to the other methods, which also change the loss function or different stuff inside. But what are the reasons, in fact, behind this accuracy gain? So now let's move maybe to some factors which may influence the encoder performance. And the first one is the fraction of the active triplets. And this plot shows the fraction of the active triplets from the batch which was created using the random sampler. And you can see that when the encoder is getting better and better, the fraction of the active triplets drops close to the 0. Using the same miner, but changing the sampler to hard class sampler, we get a much higher fraction of the active triplets in each batch. This shows that indeed hard class sampler provide higher fraction of the active triplets. And this is what may be one of the possible factors influencing the performance of the encoder. And how does it impact the loss distribution among the triplets from the single batch? So this plot shows the histogram of the triplet loss with the margin equal 0.2 among triplets sampled from the random sampler and hard class samplers. To create this plot, we use the same encoder, which was the fixed, and just change the sampler. And as we can see, the hard class sampler produce less triplets with the margin below 0.2 and more triplets with higher values above the margin compared to the random sampler. And this means, from interpretation, that is more often it produces the triplets where the negative is closer to the anchor than the positives. And to justify it, we have also the distribution of the anchor negative distance. This is the top right plot, and it shows that on average, the anchor distance between the anchor and negatives for hard class sampler is closer compared to the random one. It means they are harder. However, the second histogram, the anchor positive distance, require more comments, in fact, because not only the negatives are closer to our anchor, but also the positives. And such behavior was not designed in our hard class sampler, as choosing the positive pairs is the same exactly like in the random sampler. So this requires maybe some short explanation. So let's analyze which positive items participate in the active triplets, depending on the location of the negative items. So this picture shows the anchor and the 3 positive items. And the dimension is the distances between them. The arrow is just the margin from the triplet loss. And if the negative is where this red dot show, only this more to distant positive items create the active triplets. And this corresponds more to the random sampler, which create the easier negatives and also harder positives, because both of them are farther away from the anchor. However, if the negative is closer to the anchor, then then it produces more active triplets. And this way, in fact, the more similar negative to the anchor provide more similar positives. And interestingly, this recent publication from the ICCV also designed something like the mining strategy, which were mining the easy positives and harder negatives, which result on the better performance on the code of an encoder. From our ablation study, looks like that also the hard class sampler is doing exactly the same. It provides easy positives and harder negatives. So in summary, the hard class sampler improved the performance of the encoder compared to the random one, and indeed changed the number of the active triplets, and also changed the distribution of the distances, to which many people contribute the performance boost. However, such results leave the open question for the future research. Similarity to the other publication, we already have the empirical results showing the advantages of our method. But we are interested more in understanding the reason behind it. Is this related about this number of the triplets, maybe these distances, or maybe there is some kind of the distribution of the distances, or maybe other explanation which we are currently not aware of. And most of the paper published in the deep metric learning give only intuition, sometimes contradictory, of what is important and why. And we are interested in validating these ideas to build a better understanding of this domain. And small add at the end of the presentation, if you want to work on an interesting project and do research and like the work presented today, or maybe any other topic you can imagine of, just apply for the research engineer position at Allegro. And thank you for your attention. It was a pleasure to have a talk in this ML in PL virtual event. Thank you very much.
I am so sorry. Thank you for the interesting talk. It was a pleasure to listen to all the interesting things. And we have time for a few questions. Sometimes smaller contrastive triplet loss does not translate into better retrieval results, as it is only a proxy of the actual function that we want to optimize. How do you deal with such cases?
Okay, one thought about this is that the triplet loss on the training set might be indeed the function we want to optimize, because it's similar to a margin loss like in SVMs, but yeah, it is a proxy of what we really want to optimize, because we are interested in performance on unknown data. And actually, there is pretty little research, like not intuitive answers to this question, because many papers have like intuitions that we should use like not that hard but not too easy triplets, and this will translate to the good performance on the validation data. But there are like not many strong results about this. But maybe it is changing this year, because there were those two papers, for example, from ICML, where people were validating certain claims from other papers, and maybe those papers from this semi-supervised learning workshop. So it is, I would say, this is still an open problem, how to approach this.
Sure. Okay, thank you. Another question is, you show results compared to random sampler. Did you also perform experiments versus other sampling methods?
So maybe I will ask for this question. So in fact, as we said, in fact, there is a little research on the samplers, but in fact, there is this paper which we shared, it was divide and conquer. It's also the sampler, so we also benchmark against it. And also there were different samplers from this paper from the ICML, which was revising the ideas from the different sampling. But their ideas were pretty much about the hyperparameters of the samplers. I mean that, for example, that we can choose the 2 images from each class, or maybe 4, or maybe 6. And in fact, their baseline was pretty much weak. So in fact, we have not so much compared to the other samplers, because there are not many of them, to be true.
Yeah, but
Sure.
the sampler can be used with many minors. So yeah, that's
Yeah,
an interesting part.
that does make sense. And about the minors, another question. I am interested how the minor is implemented. It looks like it has high complexity. Is it all combinations? How long does it take to generate it? And perhaps how do you deal with this problem?
I understand that is the question related to this minor generating all possible triplets out of the sample set.
Yes, I think so.
And these are like implemented, like you embed objects only once, and then you use indices to make it in some clever way. I'm not sure about the exact implementation. Maybe Bartek, you remember?
But as I remember, because it depends, in fact, on the number of the classes, on the examples per class. Because for our experiment, compared to the other paper, we just used batch size 128. So in fact, there is not so many triplets in the single batch. So it is not, doesn't take as much time as we can think of.
But
Sure.
there's no problem with memory, because you embed things only once and then you index.
Exactly.
Yeah. Yeah, okay. Thank you. And this is the last question. Will this visual search be soon on Allegro?
Okay, I will answer this question because I'm also there from the visual search team. And yes, it will be. And I hope that in fact it will be maybe the first month in the next year. So in fact, you should be ready, in fact, to use this option in the beginning of the next year.
Great. Okay, so that's very exciting. Thank you so much. The talk was very interesting, and thank you for answering the questions.
Thank you very much.
Also, I want to thank everybody in the audience, also for very interesting questions and for taking part. And now I would like to invite everybody to the poster session. You can find the posters in the Sessions tab, and I encourage all the authors to join their poster sessions, because every poster has its individual session. You can also vote for your favorite ones, and you can find the form in the descriptions. And also, I encourage you to visit the sponsor booths I think that also the Allegro one, after this talk, everybody should be interested. So thank you very much and have a great time at the poster session, and feel free to ask questions. Thank you.